Hello. This live event is brought to you by Proceedings of the IEEE magazine. Greetings. We are a guest editorial team who worked with the Proceedings of the IEEE magazine to create a series of special issues on reconfigurable systems. So today we're going to be talking about reconfigurable systems. And I'd like to introduce first our guest editorial team, Christos.
My name is Christos Christodoulou. I'm here a professor in electrical engineering at the University of New Mexico. Welcome.
Hi, and I'm Jim Lyke. I work at the Air Force Research Laboratory.
I'm Warren Edwards. I also work at the U.S. Air Force Research Laboratory with Jim.
Hi, I'm Alonzo Vera. I'm also a research associate professor at the University of New Mexico.
Okay, so we have been, as I said, working with the IEEE on creating a couple special issues for the IEEE on reconfigurable systems. Now, I just want to give a word. If you in the audience want to go ahead and advance to the next slide. If you want to basically send questions to us, go ahead and use the chat window, which should appear on one side of the display that you're looking at now, and the editors of the IEEE will gather the questions and pass them on to us, and we'll answer those later, and we'll have a discussion. What we're going to do now, camera, is we're going to basically give a little bit of a set of prepared comments that relate to reconfigurable systems, and we'll be happy to have a discussion about it. I guess the first thing to say is that we had been looking. A lot of us, we have diverse backgrounds. I work in digital architectures, microelectronics. Alonzo also works in digital art, works in materials. Christos works in RF and microwave. We have diverse backgrounds, but we all saw this appeal of reconfigurable systems, and we noticed how the Proceedings had special issues completely dedicated to subjects like cognitive radio, even metamaterials. Lots of things have been written about FPGAs, but nothing had, as far as we could tell, been done with the general idea of reconfigurable systems. So in this panel discussion, we are going to be talking about reconfigurable systems. So I guess the first thing, go ahead and put up the slide. I guess the first thing is to talk about what is a reconfigurable system. And reconfigurable systems probably conjure a lot of visions up to the layperson, things like transformers. And that would be a type of physical reconfiguration. But what we're talking about is functional reconfiguration. So if we go to the next slide. The idea, and this is an example of a field programmable gate array, is that we start with a very sophisticated piece of silicon, but like a CD, it's blank until a user configures it. So we sort of depict this idea as functional reconfigurability. And it's about, in the case of the FPGA, a process that captures design and translates that into essentially a pattern that goes into silicon. And so this is all digital, the themes that we focused on in the special issues was how to take ideas like the FPGA and extend them into computing and RF and optical, and even things like programmable matter, which we think is the sort of futuristic limit of reconfigurability. And I guess one of the first things you say, well, that's very neat, but why bother? I mean, so this reconfigurability seems like an interesting curio, but why have it? And I guess the first point is flexibility is very important, especially in the 21st century. It's an enabler like no other. The idea that I can take something inside of a system and send information into that system and have it fundamentally alter the functions of a system is a very powerful idea. This idea of I call it X on demand, means that we can develop systems much faster. A field programmable gate array is already built. We can program it as fast as we can think and turn those thought patterns into ones and zeros. Another powerful idea with reconfigurable systems is that we can reduce the inventory. So we can use one field programmable gate array or a small family of these to replace many parts. And so this allows us to collapse inventory and supply chain. We can do field updates. That's very important. Systems are very complicated. So even a production system will often have many defects and software faults that are only discovered much later. And if you build a custom integrated circuit, you are stuck with that pattern. FPGAs allow you to change those ones and zeros and change and often recover functions in the field. Another idea, which is a bit more abstract, it's not used as much, but I think it will be, is the idea of resiliency. The idea that if we find breaks in the system that we can recover from those faults by reprogramming. And in fact, we have seen evidence and demonstrations of self-healing behavior where we can recover functions when a system is damaged. And finally, the idea of adaptive or dynamic reconfigurability is very, very important concept. Okay, so I've talked about why reconfigurability. Let's talk a little bit about the nuts and bolts of what reconfigurability is. How do we implement it? And on this slide, we have shown that at the top we have very primitive elements. So we have to have these little building blocks of functions, like a programmable switch, which is like a software wire, or on the right, a configurable resistance, which Art will talk about in a minute. Now we take those primitive elements, which are like the atomic building blocks, and create circuits, which is shown below. And we build programmable functions that way. And then at the bottom is this idea of a fabric. And a fabric is like a field programmable gate array, where we have an entire digital system that can be configured to implement other digital systems. So future reconfigurable systems are all about this kind of special way of doing virtualization, that I can have a blank substrate take on many different behaviors. At one level, it's virtual because we're using information to configure it, but it is implemented in real life in the functionality of the system. So now Art's going to talk about, like, if we just focus on that idea on the last slide of a configurable resistance, how do we do reconfigurable resistances? Art?
Right. So, so the memristor, which is basically a resistor with a memory, where you can vary the resistance by applying voltages, either unipolar changes or bipolar changes. This actually didn't come up because of reconfigurability, but because of a drive for very dense memory. And as you can see in the slide, there are a variety of different mechanisms used to vary resistance. Anything from growing, say, metallic paths through an insulator to changing the conductivity through electrochemistry. But a lot of them share the idea that this is a dendritic phenomenon. It's not, the whole resistor doesn't change, it's the small paths do. And as a result, it's both fascinating, but also there are problems with reliability. And so while there's this great dynamic range, what we'll see used first is binary logic. So if we go to the next slide, where we see the variety of things that a reconfigurable resistance allows us to do, the ones that are going to drive development are actually going to be the logic and memory, because those are the ones for now are going to have a very large demand. So even very dense resistive memories are going to be things that are going to drive reproducibility and say the quality of devices. But once those are realized, we're going to see a variety of things, including, as I say, threshold logic, which is very near to neuromorphic computing, but we're also going to see a drive toward using these for say, algorithms that mimic the cortex of the brain, so we can see, say, the rise of artificial intelligence, but artificial intelligence is driven by hardware instead of software.
Thanks, Art. And the idea, if we go to the slide, that we need to keep in mind with reconfigurable systems is that there are two fundamental pursuits in reconfigurable systems. And it's important as electrical engineers to understand both of these. The first of these is designing for reconfigurability. So that's the act of creating a reconfigurable system that can be used by others. And so in designing for reconfigurability, architects, for example, design FPGA fabrics. Now, most of the field actually is concerned with the other facet, which is designing with reconfigurability. So these are the thousands of people, tens of thousands of people that use FPGAs every day to do things. They're using this fabric and they expect it to work and be capable of doing what they want to do. Now, we continue to use the FPGA as sort of the poster child for reconfigurability, but extend the ideas that I'm talking about into all kinds of other systems like programmable fluidic systems, programmable microwave RF systems, photonics, and like I said, one day I believe, it may not be in my lifetime, we'll have programmable matter, material that we essentially put ones and zeros into that will do things that we want to do. So that's an important thing to think about.